Hey guys, this is Harsh Kumar, student of Alliance University CS branch, and my topic is nuclear fusion using lasers. So these are the contents we're going to be looking at: basic fusion, ICF mechanism of action as an energy source, economic viability, neutron source. Let's deep dig into these. Or- So basic fusion is reaction is when reaction combine lighter atoms, such as hydrogen, together to form larger ones. Generally, the reactions take place at such high temperatures that the atoms have been ionized, their electrons stripped off by the heat. Thus, fusion is typically described in terms of nuclei instead of atoms. The nuclei are positively charged and thus repel each other due to the electrostatic force. The Coulomb barrier or fusion barrier energy, generally less energy will be needed to cause lighter nuclei to fuse as they have less charge and thus a lower barrier energy. And when they do fuse, more energy will be released. Moving on to our next topic, which is ICF mechanism of action. I'm sorry, it was a part actually. In a hydrogen bomb, the fusion fuel is compressed and heated. With a separate fission bomb, a variety of mechanisms transfer the energy of fission primary explosion into the fusion fuel. A primary mechanism is that the flash of X-rays given off by the primary is trapped within the engineered case of the bomb. This outward blowout of causes the rest of secondary to be compressed inward until it reaches the temperature and density where fusion reactions begin. Let's move to the next part. I hope you understand this one. So, lasers as an energy source. So, basically, practical power plants built using ICF have been studied since the late 1970s. I have no idea what ICF is, but I'm gonna move on to that. When ICF experiments were beginning to ramp up to higher powers, they are known as inertial fusion energy or IFE plants. These devices would deliver a successive stream of targets to the reaction chambers, several seconds typically, and capture the resulting heat and neutron radiation from their implosion and fusion to drive a conventional steam turbine. So this is the picture of a neutron star. Basically, it's radiating energy, as you can see. So, coming on to the economic viability, how much does it cost? Even if these technical advances solve the considerable problems in IFE, another factor working against IFE is the cost of fuel. Fuel converted to better known units, this is the equivalent of 2.8 kilowatt hour of electrical power. Wholesale rates of electrical power of the grid were about zero point 0.3 cents per kilowatt hour at the time, which meant the monetary value of the shot was perhaps 1 cent. So, and to the next part, neutron source. So, inertial confinement fusion has the potential of procedure actually produce orders of magnitude more neutrons than spallation. Neutrons are capable of locating hydrogen atoms and molecules, resolving atomic thermal motion, studying collective excitation of photons more effectively than X-rays. Neutrons shattering. Studies of molecular structures could resolve problems associated with protein folding, diffusion through membranes, proton transfer mechanisms, dynamic of molecular motors, etc. by modulating thermal neutrons into beams of slow neutrons in combination with fissionable materials. Neutrons produced by ICF can potentially be used in a hybrid nuclear fusion designed to produce electric power. So basically that's about it, guys. I hope you have understood the concept of nuclear fusion using lasers. Thanks again. Hope you all enjoyed it. Thank you.